Firstly, welcome to this particular webinar, which is on application of CFD for modeling multiphase flow. It is conducted by LearnCX. Before we begin, we'll have an overview of the content of this particular webinar session. First, we'll have a short welcome and introduction. Then the entire webinar presentation will follow. At the end of the webinar presentation, we'll take any questions that you may have. And then we'll give introduction to some of our activities as an organization before we close this session. So before we begin, thank you for your registrations and for attending this particular webinar. This is an introductory webinar on multiphase flow modeling. So it will give you an exposure to various techniques involved in multiphase flow modeling and some introductory demo cases as well. This is the fifth webinar in a series of webinars which are conducted by LearnCX, and much more free webinars will follow. This webinar is designed so as to act as an introduction to multiphase flow modeling using CFD. Before we begin the technical content of this particular session, just a short introduction of our organization. We, that is LearnCX, we are an initiative of training division at CC Tech, which is Center for Computational Technologies Private Limited. We are located in Pune, India. We as an organization are involved in lots of activities, including CA consulting and CFD, CA development, as well as CFD simulation consulting activities and training activities. So what we have are basically within our training division, we have industry focused courses for CAD as well as CFD. We have an online model where we deliver all the training content through internet to the doorstep of the participant using just internet and a computer. So our model basically helps participants learn complex technologies at the ease of their time and place. So that was a short introduction to us as an organization. Now we'll begin the particular presentation, which is application of CFD for modeling multiphase flow. So an overview of the slides that are about to follow. First we'll see what is multiphase flow, why should we at all be interested in modeling multiphase flow. After that we'll have classification of multiphase flows and various types that are divided into multiphase flow is divided into various types. So we'll have discussion about those types. Then we'll have few slides which will introduce you to some industrial examples or application of wherever multiphase flow is involved. Then we'll see mathematical modeling approaches which are used or utilized in order to model multiphase flow. We'll have a short demo on tank sloshing modeling, and we'll end with summary of this particular presentation. So let us begin our session here. So before we enter into any type of discussion on multiphase flow, it is very important to understand what do we mean by phase. First we'll see the thermodynamic angle of phase definition. Within thermodynamics, phase refers to state of matter which are generally classified as solid, liquid or gases. So you can see examples of multiphase flow, or you can see examples of phase, different phases even in naturally occurring phenomena around us, like just a droplet falling into water, or even the evaporation of hot tea or hot cup of water is an example of phases which are changing from one type of state matter into other. Thermodynamically, we define phase as a state of matter which may be solid, liquid or gases. But from a modeling point of view, there is slight modification in the definition of phase. So what we say is that an obvious definition of phase is thermodynamic state, which can be gas, liquid or solid. However, it is possible to define different phases for computational purpose, although the thermodynamic state is not different. So it is possible to treat a single phase as two different phases for computational modeling purpose, as well as it is possible to define two different phases as a single phase from computational point of view. So we'll see some of the examples of that here. Even if we have dispersed gas, where solid particles are dispersed within a gas and they have wide variety of distribution, these group of solid particles can be treated as different phases if they show different flow behavior. Also, sometimes it is useful to treat two thermodynamically distinct phases as one phase for computational purpose. An example is, let's say we have a gas, liquid and solid which consist of three phase, a slurry reactor where solid particles are fine enough to essentially follow the liquid flow. So in that case, what we can say is the solid liquid mixture can be treated as a single phase, which can be defined as slurry, and then we can say that gas is dispersed in this particular slurry phase. So this three-phase mixture can be converted into a two-phase gas slurry system. So this way, from computational point of view, we have different or modified definition of phase compared to thermodynamic state. This basically comes from a point of view where we say that within computational modeling, phases are treated as different if they show different flow behavior or different velocity profiles. So if two state of matter have different velocity profile, they are considered as different phase, even if thermodynamically they are of same phase. Let's say oil and water, even though they are liquid, thermodynamically they are single state, but since they show different flow behavior within a fluid dynamic problem, they are treated as different phases. Now, since we have understood clearly the distinction between different phases, meaning that computationally how phase are treated compared to thermodynamic state of matter, we will now jump into the multiphase flow definitions. So multiphase flow, as the name suggests, involves simultaneous flow of mixture of phases such as gases in liquid or liquid in gases, and similar such applications or flows where more than one phase is involved. Even a jet of water falling into a mass of water can be considered as multiphase, as this jet is interacting with air surrounding it. Why should we at all be interested in such type of flows where multiple phases are involved? Multiphase flows are found in many industrial applications like chemical reactors, process flow industry, and many other applications wherever there are multiple phases present. Also, naturally occurring phenomena like reverse cloud formation involve multiple phases. And in practice, most of the applications will involve more than one phase, and therefore it is in such applications, in order to model them, it is difficult to isolate single phase flow from this multiple phase flow involved. So in order to resolve or model or study such type of applications, knowledge of multi-phase flow physics is extremely important in order to carry out any type of experiment or simulation on such applications. So that being said, multi-phase flow becomes a completely different field within fluid dynamics itself, and it needs separate models or separate treatment in order to simulate them. So after studying what is multiphase flow, we will see how they are classified. Multiphase flow in itself is a very vast branch of study, but these flows are classified depending upon various criteria like number of phases involved, what type of flow behavior they show. So on a broader nature, we will see those classifications here. So in order to simplify the entire study of multiphase flow, they are classified into different categories, which are mainly based on number of phases and their types. So first is dispersed phase flows. In such flows, one of the phases are in the form of discrete elements. There is no connection between these individual discrete phase elements, which may be in the form of particles or droplets. So examples of such type of flow are droplets in gas or bubbles in liquids. Even solid particulate flow within gas comes under this particular type. Then the next type is separated flows. So in such type of flows, two phases involved are separated by distinct line of contact. For understanding, we can say that we can travel from one location to another in the same phase and still remain in the same phase. There is distinct separation between two phases. So an annular flow is an example where there is liquid layer along the pipe wall and a gaseous inner core. This forms an example of separated flows, or we can also say that they are basically free surface flows, wherever there is a free surface exists between two different phases. Now the next type that we will see is gas liquid flows. These are now based on basic type of phase that is involved. So in gas liquid flows, as the name suggests, there is involvement of gas and liquid flowing together, and this can be in different forms like bubble flow and annular flow. Also, similar to gas liquid, there is gas solid flows in which there is presence of gas medium and solid medium. Examples is solid particles dispersed or suspended within gaseous medium. Granular flows are also an example within or a subtype within gas liquid flows. Then there is also liquid solid flows where solid particles are carried by liquid, which is the continuous medium. Another name or terminology for such type of flows is basically slurry flows. The most complex type within multi-phase flow is basically three-phase flows, which are encountered in many engineering problems. For example, bubbles in a slurry flow gives rise to three-phase system, and this is still an emerging topic for research as well as computational modeling. So as the number of phases increase, the modeling becomes much more complex. So this is the overall classification of multi-phase flows. After seeing the classification of such type of flows, we will turn our attention to basically some industrial examples. So what I'll present here in this particular slide is just a list of industrial examples wherever multi-phase flow is involved. So some of them are listed here, like solid suspensions, where we have suspension of solid within a liquid medium. Droplet separation is also a type of process where multi-phase flow is involved. Solid drying systems involve more than one phases. Packed bed reactors are used to enhance reactions which involve more than one phase material or medium. Foams is another example used in various chemical industries. Packed columns are used which involve multiple phases, which are mainly gas within a liquid or solid bed type of applications. Centrifugal extractors also involve multiple phases. Emulsions is an example. Mist eliminators are another example of multi-phase flow systems. Sedimentation devices are commonly used in chemical industry, involve multiple phases. Cyclone separators, which are basically used to separate materials or separate fluid based on their difference in densities, involve solid particulate flow within gaseous or liquid mediums. These also employ multi-phase flow behavior, or these also have multi-phase flows involved in them. Mixers are also another example. Bubble column reactors are a very interesting example of multi-phase flow, as well as fluidized bed systems. Particulate system involve particles within either gas continuous medium or liquid continuous medium. Precipitators are also another example, as well as dust collection systems. So when we say that multi-phase flow is present, the predominantly present phase is referred to as basically continuous medium, and the secondary medium is defined as the medium or the phase which is present in lesser extent or occupies lesser volume. So one phase is primary, which occupies the most volume, and the rest of the phases are defined as secondary, which occupy less volume. Now we'll see in detail bubble column reactors. So bubble column reactors are equipments used in chemical industry for gas liquid reactions. Some pictorial representation of that is shown here. It is built up of vertical columns of cylindrical forms, and what happens is basically gas is introduced at the bottom of the column, which causes turbulent mixing or turbulent streams, and thus provide required stirring action for reactive gas exchange. So CFD modeling of that is predominantly done. An example of a CFD model of that is shown here. As you can already see and understand, it consists of two phases, that is liquid and gas. Next example that we'll see in a bit detail is stirred tank reactor. This is designed to basically contain chemical reactions or carry out chemical reactions. It consists of a cylindrical or other shaped tank which is having a central rotary element and which causes stirring between different phases. So that's why it's referred to as stirred tank reactor. And impeller stirs the reagents, which leads to proper mixing of different phases. Example of CFD model. Example of CFD model is shown here. Next example is fluidized bed reactors. These basically have solid fluid mixture which ultimately behave as a fluid. We'll see how it happens. An example of the volume distribution model, volume distribution of a CFD result is shown here within a fluidized bed reactor. So what happens here is there is introduction of pressurized fluid through the particulate medium. Fluid is purged, or fluid is basically forced from bottom within a packed particulate medium, which causes the particles to act as suspension. So the entire system has the ability to promote high level of contact between gases and solids. Fluidized bed reactors, within those, fluid flow upward through a bed of solids. So beyond the critical fluid velocity, these solids become suspended, and the entire mixture or the entire medium will act as a fluid. So it will behave as a fluid rather than a solid packed bed. So these have lots of applications in chemical reactions, solid mixing, enhanced heat transfer, drying, heat treatment and coating. An example of a 3D model which is based on CFD analysis is shown here of a fluidized bed reactor. Now, since we have seen and generated some interest in multiphase flow applications, the main thing that is to know or understand is how do we numerically model these multiphase flow? Can we just model them by using a single set of Navier-Stokes equations, or do we have to apply Navier-Stokes equations to multiple phases? How it is done in the actual software or even in numerical codes? So, from our understanding of basic CFD or from understanding of numerical methods, we know that Navier-Stokes equations are used to model fluid flow. So for a single phase, we use a single Navier-Stokes equation and discretize them in order to numerically model single phase fluid flow. So for that we use continuity equation, set of momentum equations and energy equations. So what happens to these when it comes to multiphase flow? We will see those in the coming slides. Multiphase flow can be mainly modeled by three different approaches. First among them is Eulerian-Lagrangian approach. This approach utilizes Eulerian framework for the continuous phase and Lagrangian framework for discrete or dispersed phase. What this means is, for the continuous or the primary phase, governing equations that we just discussed for the single phase are solved, whereas for the secondary phase we just solve equation of motion. Within the Eulerian framework, which is the Eulerian model, which is the second approach, we utilize Eulerian framework for all phases, which means governing equations are solved for all phases involved. And the third approach, which is called as volume of fluid, which in short, which is termed as VOF. In this, Eulerian framework is used for both or all the phases involved, but there is a specialized interface treatment in order to track the free surface or the connecting surface. We'll see the pictorial representation of these approaches. First, we'll see what do we mean by Eulerian-Lagrangian approach. So let us imagine that there is a bulk mass of fluid which is shown by blue, and we have dispersed particle or dispersed phase, which is secondary phase, which is shown by these small dots or circles. So what we need to do is basically model the flow behavior of this continuous medium as well as the location or trajectories of these secondary particulates or dispersed phase. So the particulate or dispersed phase trajectories or path are basically solved by using equation of motion, and the Eulerian governing equations are used for modeling the bulk flow behavior for the continuous phase. Now there exists coupling of energy and momentum between the dispersed phase as well as the continuous phase. So this is taken care by using coupling models or basically force balance. Now coming to the second approach, which is the Eulerian approach, we will imagine the same system having continuous medium and dispersed phase secondary medium that is basically dispersed in this particular primary phase. So in the Eulerian approach, a control volume type of equations or control volume approach is used for each phase, for solving velocities of each phase. Governing equations are solved for both the phases. Volume fraction is also solved at control volume. So basically volume average equations are solved for secondary phase, but still those are governing equations which are solved. Those are not equation of motion. So we solve governing equations for both the phases. And lastly, for the third approach, which is volume of fluid, we have basic this particular approach is used only in case where we have distinct separation between two phases. So we have a dispersed secondary phase and a continuous primary phase. So what we do is basically volumetric forces and interface tracking is included in addition to solving a single set of governing equation. So a single set of governing equation is solved for both phases using combined mixture properties. So a type of mixture is defined which consists of averaged properties of all the phases or both the phases involved, and we solve governing equation for basically this mixture rather than individual phases. But we do interface tracking also in order to find the shape and location of this distinct interface. So after the pictorial representation, what we will see is the mathematics involved behind all these models. Just a brief overview of them. We will not go into detail of the equations, but we will have we will list the equations that are involved rather than going into detailed mathematical treatment because of shortage of time here. So for the Eulerian-Lagrangian model, continuous phase is modeled using Eulerian framework, that is Eulerian method or Eulerian form of governing equations. So equation of motion, but for the dispersed phase or the secondary phase, equation of motion is or Lagrangian method is used. Since we are not actually modeling the flow behavior of the secondary phase by using governing equations, this particular approach is possible only in that case where the flow of the secondary phase is not affecting the bulk flow behavior in detail or to a large extent. So that is possible only when the secondary phase is having low volume loading, or it is present in lesser extent or lesser volume percentage. So this particular approach is therefore possible only in case where we have the secondary phase present in lesser extent or lesser volume content. Also, whenever the secondary phase is occupying larger volume, it also displaces some volume of the primary phase. So that particular physics is completely ignored in this particular approach. Since we assume that the secondary phase is present in lesser volume, we can neglect the volume displacement of the primary phase because of the secondary phase. So these are some of the assumptions. Now coming to the mathematical treatment, we solve continuity and moment, set of continuity and momentum equation for the primary phase only, and what we do is basically for the secondary or dispersed phase, trajectories of these dispersed phase are calculated by using equation of motion. So we use Newton's law of motion, which is just the balance of forces. So this particular type of Newton's law of balance of forces is used, which considers lots of force balance involved, and this takes into account the interaction between the primary and the secondary phase. So in this we have the drag force, pressure force, virtual mass force, as well as body force. So we'll see how the process goes on. These individual forces are calculated by their configurations. For pressure force, we use the pressure gradient. For body force, we use acceleration due to gravity. For drag as well as lift force, we use the relative velocity and their corresponding coefficients. So as shown here, for lift force, we use the lift coefficient. Now there is some additional force in addition to drag and lift force, which is virtual mass force. So when the dispersed particles accelerate, some part of the surrounding continuous medium or continuous phase also accelerates along with them, and this surrounding mass which is accelerating along with them gives an effect of extra acceleration or inertia of added mass. So this gives rise to some extra force in addition to in addition to lift and drag, which is termed as virtual mass force, which is taken into account by using its own configuration and related to the relative velocity between primary and the secondary phase. So what we do is basically solve continuous flow equations for the primary phase. Then using this, we use the momentum exchange between that and find the interactive forces between the primary phase and the secondary phase, and then we calculate the velocity of the secondary phase or the dispersed particulates. After calculating the velocity, in order to calculate the path followed by the secondary or the dispersed phase, we use basic definition of velocity, that is this. So this relates velocities with respect to with respect to the location, time derivative of location. So once we know velocity of the dispersed or the secondary phase, we can find its location, and that way we actually find out the trajectory or path followed by the secondary phase. So this is how we basically use Eulerian-Lagrangian approach in order to carry out modeling of dispersed phase which is dispersed between the continuous phase. Now coming to the mathematical treatment within the Eulerian approach, in this the secondary phase or the dispersed phase is also treated as a continuous or continuum medium. Eulerian equations, that is governing equations, are solved for all the phases involved. Coupling between the phases is represented by various interface transport models. So as you can see, this is a much more resolved type of approach where we also solve governing equations for the secondary phase, and its entire flow is modeled to much more accuracy, and therefore this is basically suitable for wherever the secondary phase is present in predominant extent, that is the volume loading of the secondary phase is more than 10%. Mathematical treatment of that is shown here, where we solve continuity and momentum equation for each phase. So these are termed as phase specific governing equations, where phase volume fractions are used in wherever we have quantities like density and velocity, and we solve such type of equations for each phase. Then interface force balance is done for each phase, as well as interface coupling is used for each phase wherever we involve momentum, energy and mass transfer. So that was for Eulerian model. Now we will see a brief overview of the mathematical treatment or the process followed in volume of fluid approach. So in volume of fluid approach, flow around individual particles is resolved. So we use basically a single set of governing equation for all the phases involved. We come up with a term called as mixture properties, using properties of individual phases, and governing equations are solved using these mixture properties. It is suitable for stratified and separate flows where there is a distinct interface between two or more phases. This particular assumption that we are solving single set of governing equations for multiple phases, this does not track interface directly, so we have to come up with some special treatment for seeing the interface contact. In order to capture interface, we solve a type of advection equation for volume fraction, and hence what we do is basically we solve a continuity type of or advection type of equation for n-1 phases and find out the amount of phase involved in each particular cell or each particular location. But these advection equations are not enough. What they'll give is just the amount of percentage amount of phase involved in particular location, but they won't give you the shape of the distinct interface between two phases. So for that we use special numerical techniques to come up with the right shape and location of the interface between two phases. So in order to conclude the mathematical treatment, what we do is basically in the Eulerian approach, we solve governing equations for all the phases involved and do the interface coupling using specialized models. In the Eulerian-Lagrangian approach, the governing equations are solved only for the single phase, that is the primary phase, but the secondary phase is only tracked, or its trajectory is modeled using the equation of motion. Whereas in the volume of fluid approach, a single set of governing equations solve for the mixture properties, and the interface or the shape of contact line between two phases is basically modeled or is basically simulated using special interface treatment. So these are the distinct points in the three approaches that we have discussed so far. So after this, what we will see is basically a demo case in which we have used the volume of fluid approach in order to model separate flows or flows where two phases have distinct interface or distinct contact between them. This particular demo case is titled as fuel tank sloshing. It is applicable or it is utilized in domains like oil and gas, automobile, aerospace. The physics involved is basically transient multiple phase or multi-phase flow with free surface. Softwares used are ANSYS ICM and ANSYS Fluent for meshing as well as solving. The objective of this demo case was to investigate free surface movement between liquid fuel in the tank under varying acceleration scenarios. And we also compared effect of baffles on sloshing. Now what happens as physics is basically wherever we have tanks containing bulk volume of liquid, wherever there is change in acceleration or acceleration of that particular vehicle or that particular tank, there is sloshing happening in that particular liquid. So this sloshing is actually a two-phase flow or a two-phase phenomenon between the air present and the liquid present, and depending upon which application or where this instrument or equipment is located, this sloshing can make issues related to structural design as well as the flow, if the flow is going out of this particular tank. So in real life scenarios, this particular investigation is applicable to automobile fuel tank, where we investigate and ensure that continuous supply of fuel is happening through the pickup line, and also in oil and gas ships, etc., where we see effect of this sloshing on the structural stability of the vessels. So this application of this simulation is widely present in many domains. For this particular demo case, we have just considered, in order to just show you the application of VOF as a just qualitative demonstration, we have considered a tank half filled with kerosene fuel. So what we did is we considered a vehicle. This tank is located on a vehicle which is undergoing acceleration for the first 1.5 seconds in the x direction, and after 1.5 seconds the acceleration just stops, and for rest of the 1 second of simulation we have not considered any acceleration in the x direction. So this is sort of a tank where we have acceleration in the positive x direction. So what we do is we just apply a acceleration in the positive direction for 1.5 seconds and then reduce that acceleration value in the modeling software. But the point to note is there is gravity acting in the negative downward direction all the time, that is for the entire 2.5 seconds of simulation. We have solved basically or demonstrating you 3 cases. First case is tank without, just an empty tank or a tank without any obstructing objects. So there is a tank with volume of kerosene at this much height. This is a free surface between air volume at the top and kerosene volume at the bottom. So below this surface there is kerosene, above this there is air, and this is the free surface shape. In the case 2, we have considered basically some baffles, that is 3 baffles with 2 holes each, but the baffles are not having any thickness. So in modeling assumption is that we are not considering any thickness of the baffles. And in the third case, we are considering baffles having thickness, and also the baffles are perforated. So in order to consider the effect of area of holes, we have used the porous media model, which is a specialized treatment within CFD in order to model perforated plates or perforated baffles. Now why at all baffles are used is to basically damp these oscillations or damp these sloshing to provide structural stability, or so that the fluid volume remains as stable as possible. So this is the distinguishing factor between these geometries that were used. So in the first case we are having just a tank without any baffles, but in the second case, in this particular case, we are selecting 3 baffles with semicircular holes, 2 each in each of the baffles. And in the third case, these baffles are having array of holes. So physically it is not possible, it becomes computationally very expensive to consider these holes as they are. So we are approximating these perforated baffles into porous media, giving the thickness, but physically not, in the CFD model we are not actually modeling these holes, but including the effect of these holes. So in third case we are having thickness with porous media. So just the details of the case setup is that we are having 2 phases involved, air and kerosene. There is distinct free surface between 2 phases. Flow physics is transient and porous media model, which is additional model that we are using. It is a time dependent simulation. Total time of simulation is 2.5 seconds, that is the fluid is moving for 2.5 seconds. For the first 1.5 seconds we have acceleration in the x direction. For rest of 1 seconds we have no acceleration in the x direction, and gravitational force is acting all the time throughout the 2.5 seconds. What we have observed is these are the free surface where it is where sloshing is happening. So what we observed is in the first case where there were no baffles, maximum splashing of that particular kerosene is at 0.45 seconds at that particular instant. In the second case with 0 thickness or no thickness baffles, the maximum splashing was at 0.9 second, whereas in the third case also the maximum splashing was at 0.87 seconds. So you can observe that particular sloshing behavior. This is the free surface. So below this surface there is kerosene, and on the other side there is air. So this is how the free surface splashing is happening for case where there are no baffles. So you can see the entire sloshing. This has been done using the VOF model or the volume of fluid multiphase model. So this is how the movement of the free surface is simulated, and we can observe that in the animations. Now coming to the second case, this is how the free surface or splashing happens in the second case where there are baffles. You can see that the splashing intensity is reduced because of the presence of baffles, and the settlement of the liquid is much more compared to the first case. So there is some sort of damping provided because of the presence of baffles, even though they are 0 thickness. Now coming to the third case, we are having baffles with thickness, as you can observe here, and the damping is even more compared to the second case. So we can see that the liquid settles down pretty quickly compared to the earlier cases. Remember, below this, although we have not shown, this is the free surface, but here all kerosene volume is there, or kerosene is occupied, where at the top there is air. So this was animation in all the three cases. So we are almost at the end of this particular session. We'll summarize whatever we have discussed so far. We studied multiphase flow physics, what is phase, what are classification of multiphase, and what do we mean by multiphase flows. We also discussed in brief the mathematical models. We did not go into detail, but we presented the mathematical models and clear distinction between the different mathematical approaches. We also saw applications of multiphase flow modeling in various industrial applications, and a demo case was presented which was based on tank sloshing. So the aim of this particular webinar session was to just introduce you to topic of multiphase flow modeling and generate interest in this particular field where CFD is used for numerically simulating multiphase flow. So we hope that we were successful in just giving you an exposure of this particular application of CFD, which is quite interesting, coming from its the wide variety of utilization or the application that it has in industry, as well as the complexity involved in modeling. So this was just the technical presentation. Now we'll give you some introduction or some knowledge of our activities as an organization. So what is required in order to enter CFD field is fundamental knowledge of fluid dynamics and heat transfer. Also fundamentals of CFD from algorithm point of view. How to use any of the CFD software, how to generate mesh as well as do CFD simulation from solver standpoint, and how to use the CFD results in order to design. Since we are an organization which is involved heavily in training, we have observed that most of the training in CAE field is basically rigid to classroom, because it is mentioned that hands-on practice is required. But due to that, there is a disadvantage that the training schedule is fixed. It is basically located at a particular space limitation is there, and also the tutor or faculty limitation is there. So it becomes a much more rigid approach where these are just additional skill sets. These are not your basic degree. So these are additional skill sets that you can gain along with your professional activities and your academic activities. So what we need is a basic flexible schedule or flexible type of platform in order to gain all these additional skill set. So we provide that by using training through online platform. So for participating in our training courses, you do not need to travel. What you have to do is just have an internet connection and a PC. So we deliver all our training and personal mentoring through internet, and we have lots of materials that you can go over any number of time. You can do this course at your own time throughout the day, wherever you find time. You can log into the training system and view the courses. Also, there are interactive sessions where you get to interact with our expert tutors or faculty and clear your doubts or get mentoring or personal attention type of environment. And we have a huge set of library of lectures and tutorials. So this is basically a new type of training approach which we are developed instead of being stuck in the old times. And this online training, as you all know, is a very evolving and fast growing type of platform for delivering any type of training. So we are offering CFD training as well as CAD training and the entire CAE portfolio through online training. Currently, what type of courses do we have? We have CFD modeling using ANSYS ICM CFD and ANSYS Fluent, which is our basic flagship course. Then we have advanced course on multiphase flow modeling using ANSYS Fluent, as well as advanced course on heat transfer modeling using ANSYS Fluent. Also, in addition to this analysis course, we have computer aided geometric design courses, which are basically programming based course which teach you how to develop codes which are used at the back end of CAD softwares. New courses are coming up, and this is just a short list of courses that we have. We have courses on CFX, using CFX software for CFD modeling. We will be coming up with courses using Star CCM as a software. So there are advanced course on meshing, advanced course on combustion that are available, as well as turbo machinery modeling. So we have an entire portfolio of skill set development on a single online platform related to computer aided engineering. That's why the name is Learn CX, which means learn lots of technologies associated with CAE just by using internet. So how to reach us if you have any queries or if you have any training needs is basically through our website, that is learn6.com. You can also visit our blog as well as connect to us on Facebook or Twitter. We have YouTube channel where there are free resources available. But if you have any doubt whether you need some sort of minor free guidance, or if you want to get involved or participate in our paid courses, you can email us at info@learncx.com. We have our technical support faculty or tutor faculty which will interact with you in order to resolve your queries through email. So this is the best way to get in touch with us, info@learncx.com. So we are at the end of this particular session, and we will take your questions. If you have any questions here, you can post your questions in the chat box. So thank you for attending this particular session, and hope you enjoyed this particular session and also got some new knowledge and some exposure to a field that will generate interest later on. So that was the purpose of this particular session. So we are ending this particular session. Thanks again for participation. We are open to questions in the chat box.